Okay, if you've missed your nap, then this is the place to be. So, alrighty, let's get started. I'm Jim Duey. There's my Twitter handle and my blog. And this is Live Free or Die. And I work for Viasat, great company. So yeah, this is not a talk about New Hampshire. This is a talk about the free applicative functor. And it says the free monad, which they're very similar. But as I was writing the talk, and as I've been working over the past month, the applicative functor is much more, it's simpler and seems to be more useful. So I did a bait and switch on you a little bit. Alrighty, free functors. This is the definition you can find pretty easily of a free functor. Yeah. Anybody understand that? Does anybody know what that means? You can just raise your hand and then come up and give the talk. Because I don't understand what it means either. I don't even know what those words mean. So let's review a little bit about what monad is. Monads are really pretty simple. They only have 3 parts. A wrapping data type, so it's a data type that holds any value of any other kind of data type. A function that takes a plain value and wraps it, and a lot of times those are called return or result. And then a function to apply to take a wrapped value and apply a function to it. And that's often called bind or flat map. And so you can see the signature for it. The x is a wrapped value. Inside the parentheses is a function that signifies a function that takes a plain value and produces a wrapped value, y. So then flat map takes those 2 parameters and gives you a wrapped value back. That's all it does. So a free monad, all it is a way to use flat map, that flat map function, to create a nested data structure. That's all it is. And then there's a function pure, so if you have a nested data structure, you have to know when you bottom out of that data structure, or the leaves of the data structure. So you wrap the values that are your leaves in pure. Use the pure function to indicate those. And then once you have this data structure, then you need to get an answer from it, and so that's the evaluate function. And we'll look at that evaluate quite a bit later on, because that's where all the magic happens. Okay, so that's the free monad, and I'll give you some links to read more about later. So then reviewing what an applicative functor is. It also has 3 parts. A wrapping data type, just like the monad. A wrapping function, which is essentially the same function as the result or return, just is often called something different. And in this case, wrap is what I'm calling it. And then also it has an applying function. And here's where the difference shows up between the applicative and the monad. So the fapply function takes a function that has been wrapped in the applicative data type, and then any number of args that are also each individually wrapped in that data type. And so fapply knows how to take those, unwrap all of them, apply the function to the various args, and then wrap the result to give it back to you. So that's what fapply does. Once you kind of get familiar with working with that, it's really just straightforward and makes total sense. So let's look at a little bit of code. I'm a closure bigot, just so you know. S expressions are the one true syntax. So I make no apologies. So this is how I defined the fapply function. And because of the way Clojure's dispatch works, type dispatch, I use a helper function, fapply star. And so fapply just takes f and then arg and the rest of the arguments and wraps the f with the same kind of wrapper that the arg has, and then just calls fapply star with the wrapped f, and then the arguments all appended together in one list. So that's all fapply does. It's just a wrapper around fapply star. So the free applicative, as you may guess, it uses the fapply to create a data structure. And that is all the free applicative functor is a way to create data structures. It also used that same pure function to indicate the leaves of your data structure, and also use that same evaluate function to interpret that data structure you've created and to get the actual answer that you want. Okay, so here's some code. And this is how you implement the free applicative in Clojure. So def type is the way Clojure does record types. And so on the left, we're defining the pure record type. It holds one value, v, which can be any value. And it implements the applicative interface, which is the two functions wrap and fapply star. And the only thing it does with wrap is it takes the new value v and just creates a new record structure. And then with fapply star, it calls that free app function, which is defined in the lower right. And all that function does is create a free a record type, which is defined over there on the right. And then the lowercase pure here at the bottom left is just a little nicety to wrap around the pure constructor. So that's all it is. That code is not complicated, very straightforward, has some really surprising implications, as we'll touch on later. So that's that. So let's do a little code action here. Oh, I left that. So if we define a pure value that holds a keyword a, you would know it. Oh. No matter how many times you run through your presentation, you forget something. There we go. So that defined the value a, and it's a pure record that holds the keyword a. And so if we print it or examine it, it just shows pure a. It's kind of a pun. And also, when you do your presentation in your head, you don't hear those kind of things. So fapply, and we'll just use list as a stand-in for any other function. You can put any function here you want. And we'll apply list to a, and we'll make another pure record type, b. And then if we examine that, you see it's just a free a record, which holds that whole nasty stuff is the way Clojure prints out the name of a function. And then the pure a, pure b. And you can do another one. And you'll see how it's kind of building up that data structure. One more. So there we have, and it's really just a tree data structure. And that's what it looks like. Can you show what? Oh, I didn't. Mistyped. There you go. I intended to do that, so thanks for catching that. So this is another way to visualize that data structure. It's just a simple list, or a simple tree data structure. The leaves are the pure values, and the interior nodes are the free A type records. And they contain the subtrees in them. That's all it is. That's the free applicative functor. Okay, so the interior nodes were all of that free A type, and they were created by fapply. But if you want to add information to those interior nodes, you need a way to do that. And you really need that kind of capability in order to do a whole lot of useful stuff with this. So you could take any record type, any def type, and put it inside that at an interior node, but it would need to implement the same applicative structure. And so, and you kind of become free, so to speak. So here is some code for the free record type. And again, it just implements the applicative interface and also has a nice wrapper to look nice. And then that V that the free record type wraps around is your def type, is your custom def type that you can put anything in there you want. And so then it becomes, once you wrap it in free, then it can become the interior node of that tree data structure that you build up with fapply. Okay, so let's look at an example, HTML, a nice tree structured thing. Just review, an HTML tag has 3 parts: a name, a list of attributes and associated values, key value pairs, and a list of content tags. So it's a recursive tree data structure, and you can have none or multiple content tags contained inside one tag. So seems so simple, doesn't it, until you start to work with it. Okay, so the simplest thing that'll work, the def type for tag, and it just contains those three things. So this code is going to take a little bit of explanation, but it's really easy, simple. The top function, pure value, just takes V, and since closure is dynamically typed, that can be of any type. So it takes V and just checks to make sure that it is either a free A, or a pure type. And if it is, then just returns, it doesn't do anything to it. But if it's not one of those 3 types, then it just wraps it in a pure and says this is going to be a leaf. And that's really, the only reason that's in there is to make the DSL that we'll see a little bit later just a little prettier. So it has virtually no real, otherwise you just have to put that pure in there every time you use it. Okay, so the tag function is a little more complicated. How many of you guys are familiar with functional programming, by the way? Excellent. Love FP. Okay, so this is pretty standard stuff. Tag is just a function that takes one parameter, and it returns a function that takes one attribute hash map, essentially, and then a variable number of content tags. So that's that signature for the anonymous function down there. And then it just maps the pure value up above over the content tag that you gave it to make sure that they're all free data structures. And so once that little bit of processing is done, then it just creates a tag record with the name that it's given, the attribute hash map, and then it uses free app to create an fapply or a free A data structure, like we saw before, of the function list, which it wraps in a pure, and then the contents. So what comes out of that call to free app is a tree data structure. And then that subtree is embedded into the tag record as the contents. So this is how you use that little DSL. Define a couple of, 5 special cases for the different HTML tags. And then I am not a web programmer, so I just hacked together an easy page thing. And the curly braces are how Clojure does hash maps, and so hash map literals, and so those are just empty hash maps. And for this talk, I'm totally ignoring the attributes value. It'd be easy to deal with them later, but I just don't have time. So you can see that you can just pass your strings for your content, and that pure value, or the pure value function, will go ahead and wrap them in pure. So the strings are the leaves of this little tree structure that we're building. And the other things are the interior nodes, the subtrees. And then that all gets packaged up, and page then holds the root of the tree. Okay, now for the magic. So you have this nested tree structure, and now you got to do something with it. So you evaluate it. Okay, now here's the magic of free applicative functors. Is this data structure that you have, that you've created with the free applicative, can be converted to any other applicative functor value. And there are a number of, actually there are probably a large number, but there's a number of useful free applicative functor values, or applicative functor types. First of all monads are also applicative functors. So if you want to take this data structure that you've created and turn it into a monad, you can convert it into any monad, a value that's in any monad. Or there are some applicative functors that aren't monads. You can also have converted into them. And then once you've converted it, then you can evaluate the value that the concrete value that you've evaluated this into. You can interpret that value and get the answer that you're looking for. So that's what evaluate does. So let's look at some code for that. Defining a protocol, this is just how Clojure defines an interface. And so the evaluate function that's in the free proto interface takes 3 parameters. It takes the free value itself, which is the data structure, the tree that you're going to be evaluating. And remember, we had 2 kinds of nodes in our tree. We had the leaves, which were all pure, and we had the interior nodes, which were free, that had been wrapped by that free thing. And then we also had the f-applied, the free A interior nodes. So evaluate itself takes care of the free A types. But you need to give evaluate functions that tell it how to deal with the pure values and the free values. And so that's what eval pure and eval free are. They're just functions that will take a value from inside of a pure or a free record type and do something with it. So that code before I showed of the pure record, we need to extend that so that it implements that evaluate or the free proto interface and give it an implementation for the evaluate function. So it ignores the other two parameters and just takes that eval pure function and takes the value v that it wraps and calls eval pure with v. And then whatever value is returned from eval pure is what becomes the return value of that call to evaluate. So again, nothing rocket science, just simple. Free is almost exactly the same. It just uses the other function that you're passing in. Then free A is a little more complicated. I'm kind of munch things together to get them fit on the slide. But so what it does, now remember, evaluate takes it's 3 parameters and returns a value that is in whatever concrete type that you're going to, because eval pure and eval free have to return a value in that concrete applicative functor type. And remember that applicative functor type, they all implement the f-apply star function. So the first thing we do is in a free A structure, we have the function that's been wrapped, and in the free stuff, and we have the list of arguments, and each of them have been wrapped in the free. They're each subtrees. So we just call evaluate recursively on the function that's been wrapped, and it goes off and does its magic and evaluates that subtree, and the result that comes back has to be a function that's wrapped in some kind of applicative functor data type. And then we just call evaluate on each of the individual arguments, and those subtrees get evaluated, and whatever answer they bubbles back up. So now you have a function that's wrapped in whatever applicative functor type that you want, and you have a list of arguments that are also all wrapped in that same applicative functor type. So then you can just call fapply star, and it knows what to do. That functionality is just embedded in whatever implementation of fapply star is for that particular applicative functor. Okay, so eval pure takes a plain value and returns an applicative functor value that a concrete one that you're targeting. Eval free takes a record value, one of your user-defined record types, and returns an applicative functor value. And then evaluate takes those two functions and the free structure and returns a single concrete value in whatever applicative functor that you're targeting. Okay, so now let's go through a little bit of code to take all that verbiage that I spewed and make it a little more concrete. The first thing that you need when you're going to interpret an applicative or free applicative data structure is you need a data type that implements fapply star, because you're going to convert all the values in the tree into that data type. And I want to convert, take that HTML page and produce a string out of it. So I just create this little record type that is just an HTML string, and S is just a string. So this just wraps a string and then has an implementation of fapply star, so it knows how to do it. And in this case, I'm not even paying attention to whatever function that was that fapply star was given. I'm just taking the arguments that are all strings as well, that are wrapped inside HTML string, unwrapping them and concatenating the strings together, and that becomes the result of that call to fapply star. So it just concatenates the strings and then wraps them again, wraps the resulting string back into the HTML string record type. Any questions about that? Is that pretty? Oh, .s is just Clojure's way of getting to the record, the value inside. So like S up there in the parameter in the constructor that's the record name or the record label, and then .s just extracts that value out. So arg down in that call to .s is an HTML string record, and then calling .s on it. It's a getter. Sorry, verbiage again. Yes, .s is a getter. Thanks. Alrighty. So then you need because we have this tag record type, and we need a function that we can add or extend that record type to implement to generate HTML strings. So that's the def protocol HTML. And then define a little helper function for us, make HTML. And all it does is takes one of those free data structures, tree structures, and calls evaluate on it with a couple of anonymous functions that just do their thing. Okay, so the first one is eval pure, and all it does is takes a value, any value v, and turns it into a string, and then wraps it with the HTML stir wrapper. That's all eval pure does. So every leaf in that tree data structure that is your HTML document just gets converted to a string and wrapped in HTML stir. And then any of the interior nodes, which are subtrees, we just call HTML stir on them, and that's going to produce a string, and we'll see that on the next slide. So HTML stir just produces a string from a tag, and then we just wrap it into the HTML stir again. Okay. So now we extend the record type tag, and this is where all of the work happens. Everything else is just very simple boilerplate with the free applicative. This is where the work happens. And you can tell that it's really a whole lot of work. So we extend the record type tag with the HTML protocol and implement the HTML-stir function so that it takes a tag record. And the first thing it does is it just makes HTML out of the contents. It gets, using the contents getter from the tag, just gets the contents and turns that into an HTML string. And then do a little bit of replacement to make the formatting look a little bit nicer. And then we just get the name of the tag and build our little XML structure. And I'm ignoring the attributes. You could jam that in there really easily if you wanted. But then the slide would be too long to fit. So, and that's all it is. It just builds a string out of the components. So you have your nested structure. So it evaluates the contents, which works down the tree, evaluates the subtree, takes the resulting string, jams it in between two XML tags, and passes that up to the next level. And so remember, make HTML calls evaluate recursively. So you have a little bit of mutual recursion there to walk your tree and to produce the values, and then the results just bubble back up and then pop out at the top. So, and I have page in here, so page, that's what it looks like if you just print it. So let's evaluate it. Make HTML, page, and there it is. So, and then the formatting, yeah, is a little jacked up. I didn't feel like investing that much time in, I hate bit tooling, that kind of stuff. Okay, so you're going, okay, that's a neat parlor trick, but really it's kind of boring. Nobody laughs, so it means you really think it's serious. So, and I agree. That, I mean, it's just kind of like, yeah, whatever. I can do that a couple other ways and not have any problems. The thing that kind of excited me is you don't have to just concatenate strings. You could use the reader monad, for example. And so you take your XML, your HTML page, that page value, and instead of converting it to the HTML stir type, which is just concatenate strings, it converts it to a type of the reader monad, which what that is a function that takes an environment. So you take your page, evaluate it to the reader monad, which produces a function that takes an environment, pass an environment into that function, and then it goes through and produces the HTML, and any place, then you can put a little value in, and it reads the environment and inserts the value into your HTML. So it dynamically generates your HTML. So you can build a template, is the word I'm looking for. Build an HTML template, convert it into a reader monad, pass the environment in there with the template values, and it produces your HTML. So you can have a simple template, HTML templating language in like 20 or 30 lines of code. Or you can convert it into a writer monad, and it will keep track of operations that it's doing while it's evaluating the tree. And that's kind of cool for HTML, but what really got me excited was working with parsers. I did a free applicative, and it's on my blog. I did a free applicative of a parser combinator library. And so basically what you did is you defined your grammar, and that produced a free applicative structure. And then I interpret it, evaluate it one way, and I get an actual parser that will go out, you pass it, it's a function that you pass it a string, and it parses it and gives you the results back. But you evaluate it another way, and it actually prints out the grammar, the EBNF grammar. And it's the same code. I mean, you only have to write your grammar once, and you can get two forms of it. Or you could evaluate a different way and get an optimized version of the parser. And so what this really gives you is the way to write a DSL to let you solve your problem, and then you can do all kinds of things with that code that you've written once. You can evaluate it in different ways to pull more information, get more leverage out. And that's really the exciting part. I'm also doing a compiler, a closure-type variant, compiling it to C code. And so I put the AST into I use a free applicative to hold the AST. And then I can evaluate it. I write an evaluate function that produces the C code. It's like, okay, that's kind of cool. Or I can write an evaluate function that does static analysis, like type checking or optimization, and that kind of stuff. And it's all just a matter of writing a different evaluate function. So that's kind of that's the stuff that, I mean, when the things started firing, I was like, oh man, that's so cool. Keep me awake at night. So thank you very much. There are some links. The slides are at the bottom link, and then a couple of entries in my blog that explain free applicatives and free monads and some other things. So we've got a few minutes, so questions for those of you that are still awake. Alrighty, well, feel free to come up and talk to me later, and thank you very much.